Welcome to part 10 of my series of presentations about the best methods to convert aldehydes into secondary alcohols. This video is about the Friedel-Crafts alkylation of arenes and heteroarenes by aldehydes, a reaction sometimes also called hydroxyalkylation. Until recently, this reaction had only rarely been investigated in academic laboratories because it is difficult to control and predict. But with the discovery that enantiomerically pure amines can catalyze this reaction and sometimes yield enantiomerically enriched alcohols, the Friedel-Crafts alkylation suddenly attracted great academic interest, despite the fact that most products are extremely labile and not very useful. The Friedel-Crafts alkylation by aldehydes is a normal electrophilic aromatic substitution of hydrogen. Thus, electron-rich arenes and heteroarenes react quickly, while electron-deficient arenes often do not react at all. The regioselectivity is similar to that of Friedel-Crafts acylations, which I discuss in another video. Unfortunately, secondary benzylic alcohols, in particularly those of electron-rich arenes, readily form carbocations under acidic conditions. These carbocations can react with the starting arene or the product, or be converted into styrenes. Unlike the products of the Friedel-Crafts acylation, however, the products of Friedel-Crafts alkylations are more reactive than the starting arene. The initially formed product can therefore be alkylated several times. If such products form carbocations and alkylate other arenes, oligomers can be formed. For instance, one of the first synthetic polymers was bakelite, developed in 1907 by polymerizing phenol with formaldehyde. Thus, if clean monoalkylations and secondary alcohols are the target, the reaction must be performed under carefully controlled conditions. One group of aldehydes that give particularly good results are aldehydes with electron withdrawing groups. These will destabilize benzylic carbocations and thereby prevent the formation of diaryl methanes. Examples include chloral, glyoxylates, alpha-ketoaldehydes, 2,4-mylpyridines, and formaldehyde. The main advantages of the Friedel-Crafts alkylation by aldehydes is that most starting materials are readily available and inexpensive, and that the reactions do not generate any waste. The reaction conditions are often mild, and catalysts have been developed for highly stereoselective Friedel-Crafts alkylations. Unfortunately, the scope of this reaction is narrow, and a large number of side reactions can occur. Finally, most products are unstable and can usually only be used as synthetic intermediates. One important product that can be prepared by Friedel-Crafts alkylation is vanillin. For this purpose, guaiacol, that is 2-methoxyphenol, is alkylated with glyoxylic acid, and the product is oxidized and decarboxylated. On this slide, the reaction of guaiacol with formaldehyde is shown, which unfortunately only gives a relatively low yield of the required 4-hydroxymethyl-2-methoxyphenol. 2 or 4-hydroxymethylphenols are, by the way, very unstable products and tend to polymerize already at room temperature without any catalyst. This here is an attempt to moderate the reactivity of aluminum bromide by addition of pyridine, but still, the formation of the triaryl methane could not be completely suppressed. In this interesting example, an electron-deficient arene, namely terephthalic acid, was hydroxymethylated with formaldehyde in fuming sulfuric acid at 135 degrees Celsius. Despite these violent conditions, the product wasn't alkylated further or oxidized. This example is not really a Friedel-Crafts alkylation, but the hydroxymethylation of an intermediate aryl ruthenium chelate. Nevertheless, it is surprising that no second hydroxymethylation occurred, despite the excess of formaldehyde. This here is an example of enantioselective hydroxyalkylation of a very reactive phenol, catalyzed by a quinine-derived thiourea. The authors proposed that the reaction proceeded through a 3-molecule hydrogen-bonded complex of the two starting materials with the catalyst. Again, this is no true Friedel-Crafts alkylation, but the addition of a lithiated arene to 4-chlorobenzaldehyde, as discussed in the first video of this playlist. The unexpected high acidity of the arene was caused by the 4 fluorine atoms. Similar reactions have also been reported with other halobenzenes, such as pentachlorobenzene, and with various heterocycles. It is remarkable that the Cannizzaro reaction of 4-chlorobenzaldehyde was much slower than C-C bond formation, and that the product wasn't oxidized to a benzophenone by the excess aldehyde. So, what are the potential side reactions of Friedel-Crafts alkylations? Under basic reaction conditions, which sometimes work well with phenols, the product can be oxidized if an electrophilic aldehyde is used in excess. Treatment of phenols with formaldehyde in the presence of tertiary amines and magnesium chloride is actually a practical method for the preparation of salicyl aldehydes, as shown here. A further potential side reaction is the reduction of the benzylic alcohol to an alkane. This can happen because hydrates, hemiacetals or acetals of aldehydes are good hydride donors and are able to reduce carbocations by hydride transfer. With alpha-beta unsaturated aldehydes, there's always the risk that a given nucleophile undergoes conjugate addition to the electron-deficient olefin. In this example, a substituted pyrrole added enantioselectively to the double bond of a cinnamic aldehyde, catalyzed by a proline derivative. Under harsher reaction conditions, products of deformylation of benzaldehydes have been occasionally observed. Here, for instance, the reaction of benzaldehyde with toluene yielded benzene, among many other products. Deformylation products can result from the acid-mediated dearylation of triaryl methanes, as shown here. The reduced diaryl methanes are formed by reduction by hydride transfer from a triaryl methane. The latter are good hydride donors because the corresponding carbocation is well stabilized. Then, as shown on the previous slide, other byproducts from the Friedel-Crafts alkylation of arenes by benzaldehydes are diaryl methanes and anthracenes. Intermediate carbocations can also react with other nucleophiles present in the reaction mixture. And if hydrogen chloride was used as catalyst, benzylic chlorides are sometimes obtained. Here are a few further examples and review articles to help you get an overview.